అంటే మీకు ఇది తెలుసా? ఆత్మకని తెలుసా?
Good evening. Thanks for joining. Please wait for 2 more minutes. Okay, so let us start today's session. Welcome to the ninth week problem solving session for the NPTEL course Wastewater Treatment and Recycling. So, those who don't know me, for those who joined new today, let me give a brief introduction about me. I am Saravanan, PMRF scholar from NIT Tiruchirappalli in Civil Department, and I am taking this course as a part of PMRF TA-ship. This is my fourth subsequent session on NPTEL PMRF TA-ship. I have already taken air pollution control, solid waste management, as well as plastic waste management in NPTEL in the last three subsequent sessions. And this session, I am taking this wastewater treatment and recycling, and we are in the ninth week, right? So first 8 weeks we have discussed about the basics of wastewater, why the wastewater treatment is required in the first session, and in the second week we have discussed about how much we need to know the quantity as well as the quality, right? So the second week we have assessed the quantity of wastewater that is generated based on the population calculation, right? In the third week we have discussed the natural attenuation of process of the river when we are discharging any wastewater without treatment or after treatment in the water bodies, how the treatment natural purification is happening. That's what we have discussed in the third week. In the fourth week we have discussed about the treatment concepts and principles based on the reactors, and the kinetics we have discussed about the reactors, some batch reactors, continuous flow reactors, plug flow reactors we have discussed, right? And in the fifth week we have started with the primary and the preliminary treatment option. That is, first one is the let me take the pen. So first is the wastewater that is coming into the treatment plant. It will go through the screen. It may be a bar screen or a fine screen or a micro screen, and then it will go through the grid chamber. There the inorganics, the readily settleable inorganics will settle. It will pass through the primary settling tank. There all the settleable organics will settle. So all the inorganics and the organics that is suspended got removed. Followed by that, these are all preliminary and primary treatment. In the 6th week, we have discussed about the secondary treatment, that is aerobic treatment. In that, we have discussed about the ASP, activated sludge process. So there we have a aeration tank followed by a secondary settling tank. Here, all the dissolved organics are getting bigger flocks by the digestion with the microorganism, and the microorganism flocks will get settled in the secondary treatment as a settling tank. So this is a aerobic secondary treatment plant. If you think about the anaerobic secondary treatment plant, we have a digester, fluidized bed reactor, UASB reactors, and then biogas production and all we have discussed, right? And in the 8th week, whatever the sludge collected from the secondary, primary, and the preliminary treatment, the sludge management we have discussed. How to dewater, how to condition, how to dry, that and all we have discussed in the last week. This week, we are going through the advanced treatment of wastewater. After doing the preliminary, primary, and secondary, we are moving into the advanced treatment. What is left with us now? All the big particles removed here, all the settlable inorganic settled here, all the settlable organic settled in the primary settling tank, all the dissolved organic got settled in the aerobic and anaerobic process. What is not removed now? Dissolved inorganics and some microorganisms or pathogens. So this need to be removed. For that, we need a advanced treatment systems. Right? You got the whole process of this 9th week session. We are going into towards the tertiary or advanced treatment of wastewater. Here we are going to discuss about the nutrient removal. Another one is nutrient. Nutrient is not yet removed. Nutrient in the sense N and P, nitrogen and phosphorus. So we are going to discuss the nutrient nitrogen removal, phosphorus removal, and we are going to think about the adsorption process and membrane process, and then ion exchange process, finally advanced oxidation process and disinfection for pathogen removal. So this is what the content for today's lecture. Okay, so first is the nutrient removal. So what is tertiary and advanced treatment? Beyond secondary treatment, we have some recalcitrant pollutant, that is removal of stubborn contaminants need to be done, which is left over with the primary and secondary treatment. We need a stronger and more advanced treatment unit. Why we are doing this? Because we have a effluent standard quality described by different countries. They have a bylaws in the local area. So to meet that standards, we need to do some more advanced treatments, right? Yeah. So see the whole typical system here. The raw sewage is coming in after preliminary, that is bar screening. It is pumped into the secondary primary settling tank, and then if you want, you can add some equalization tank or neutralization tank. Then aerobic secondary treatment, that is activated sludge process is happening, followed with secondary clarifier. Again, a equalization tank. Then we are going with the tertiary treatment systems. It can be a membrane filter, it can be absorption filter, it can be ion exchanger, anything we can do. So after preliminary, primary, secondary, we are going with the tertiary treatment. So here, the biological treatment system can produce high quality effluent. We can get 85 to 95% removal here itself. But remaining 50% requirement, we need a further treatment. For that removal also, we need a tertiary treatment applications, right? For the designated applications. So see here, first is removing the floatable materials. Then primary treatment, removing the solids by 60% and BOD by 35%. BOD is the organics. Then the secondary treatment, removing the organics by 85%. Finally, the advanced treatment reduces it to 95% and more, even more, along with the nitrogen and potassium removal. That is nutrient and phosphorus removal is left with the secondary treatment that can be done with the advanced treatment. You got it. Finally, before disposal, we can go with the disinfection, and then for the treatment plant, we need a sludge management system. What the tertiary treatment will focus on? The recalcitrant compounds, nutrients, fine suspended particles, that is dissolved organics. If even it is fine, then recalcitrant organic compounds, emerging pollutants such as pesticides, pharmaceuticals, healthcare and personal care products, that is called PPCPs, personal and pharma and personal care products. And then dissolved heavy metals, resistant microorganisms need to be taken care in the tertiary and advanced treatment systems. Why? To provide additional treatment, and also to match with the regulatory standards, and to protect public health and environment. This is the major objective of the tertiary treatment, right? What can be done? What can be done in the tertiary treatment? Total suspended solids will be removed, total specific and inorganic constituents will be removed from the water, such as emerging contaminants, and then residual nutrients, nitrogen and phosphorus will be removed, pathogens will be removed, TDS, that's a major concern again. Inorganic, that is dissolved inorganics, need to be removed. So we can do with nitrogen removal, phosphorus removal, solids removal, organics removal, dissolved solids removal. Finally, we will go with the disinfection and effluent disposal. See here, again, you can zoom in and what can we do here? You see, nitrogen removal, we are going to discuss about the nitrification, denitrification, gas stripping. In the phosphorus removal, we are going to see the biological as well as the chemical phosphorus removal. Solids removal, we are again going to use the chemicals for precipitation. Organics removal, we can use adsorption or advanced oxidation process. Dissolved solids, we can use the membranes or other techniques that's based on driving force. We can split into electrodialysis, nanofiltration, reverse osmosis. Finally, we can use this reject water with the residuals that can be disposed according to the standards. You got it? Yeah. So what are the approaches we can do? One is physiochemical, like membrane process, adsorption, ion exchange, or some of the physiochemical process of tertiary treatment. Or we can go with the biological treatment. Even the nutrients such as nitrogen and potassium can be, phosphorus can be removed with biological systems only. In ASP itself, if you give more oxygen for more time, that is what we say as extended aeration system, right? In ASP itself, if you do a longer retention time with more oxygen addition, even nitrogen after carbonaceous BOD, nitrogenous BOD will also get removed in ASP itself. But due to the limited oxygen supply and the optimum retention time, we are going with the advanced treatment system, the same biological system we are using for nitrogen removal. Got it? And then what are the selection of this method is based on the installation, operation and maintenance cost, degree of treatment. If you want 100% improvement, you can go with the membranes. If you want a 95%, you can go with adsorption. Like that, based on the degree of treatment, technical suitability and reliability of the method, we can choose the techniques, right? First is nutrient removal. What are the nutrients? Major we are focusing on nitrogen and phosphorus. Excess nitrogen and phosphorus will cause eutrophication. That's what we are discussing from the first week onwards. Eutrophication. What will happen whenever there is excess of nitrogen and phosphorus is there? The algae that is present in the water will start grow by utilizing these nutrients, right? So the algae will form a green blanket over the water surface and it will resist the sunlight percolation, and also it will take all the oxygen in the water for its survival. So the oxygen depletion will happen in the water body whenever it is less than 4 milligram per liter. All the aquatic organism like fishes and will all die. So eutrophication is a problem based on the nutrients, right? So nutrient pollution create a dead zone. That is the zone we have discussed in the natural attenuation process, right? We have 4 different zones. So before clear zone and the regeneration zone, we have a dead zone. That is called hypoxia condition, where there is no oxygen for the survival of the aquatic life. That's called algal bloom. So that we need a acceptable nitrate level before reuse and recycling. That need to be done with this tertiary treatment. Why remove nutrients? Again, it creates toxins. Algal bloom is toxic, but nutrient is not toxic. But nutrient will produce a secondary product, that is the algae, that will be toxic. It will kill the fishes. After being consumed by small fishes, again these toxins move up to the fish chain. Like the small fishes will be eaten by shellfish, like that it will bioaccumulate in the food chain. So it will also block the sunlight and clog the fish gills. So that is again it will not respirate and it will die. So how to remove the new nitrogen? How to remove the phosphorus? Nitrogen will be present in the wastewater, typically in the form of ammonium nitrogen and organic nitrogen. We have 4 types of nitrogen. First is ammonia nitrogen, that is NH3N. Then organic nitrogen, that is organic nitrogen. Third one is nitrate nitrogen, NO3. Fourth one is nitrite nitrogen, NO2. Finally, we have nitrogen gas. So in wastewater, whatever we are discharging, that will be having ammonia, nitrogen, and organic nitrogen. We need to convert this into nitrate, then to nitrite, then to nitrogen gas. It will be emitted into the atmosphere. You got it? Whenever you are adding oxygen, NO2, then NO3, initially nitrite, then nitrite, it will go, then it will go to nitrogen gas. So this is the process of nitrogen removal we will do. Also, we can skip one process and the new process are also coming, that we will also discuss. Okay, but basically in wastewater it will be in the form of ammonia, nitrogen, and organic nitrogen. First, we need to do nitrification and denitrification. That is, nitrification is addition of oxygen to convert ammonia, nitrogen into nitrite and nitrate. Then denitrification is conversion of nitrate into nitrogen gas. That is called denitrification. One is aerobic process, another one is anaerobic process. Aerobic is nitrification, anaerobic is denitrification. This is the biological method. Ammonia stripping is chemical, physicochemical method. We will add chemicals to remove the ammonia from the wastewater. That is called physicochemical method, ammonia stripping. Okay. Second is phosphorus removal. Phosphorus, there are again two methods. Biological phosphorus removal by we will say phosphorus accumulating organisms like PaOs we can use, or chemical phosphorus method. We will mostly use chemical phosphate methods in the removal of phosphorus. Okay, typically it's in the range of 15 to 35, 10 to 20 milligram per liter. Phosphate is in the gram of 44 to 8 milligram per liter. Please remember. Also, the biological nutrient removal is called BNR process, biological nutrient removal process. Okay, see the whole chart as I mentioned. Organic nitrogen will be converted into ammonia nitrogen by mineralization process. This is a mineralization and assimilation process. Mineralization is organic nitrogen to ammonia. Ammonia to organic nitrogen is assimilation. You got it? What we are getting in our body is assimilation. Again, conversion is called mineralization. Ammonia converting to nitrate is called nitrification. Nitrate, when it's converted to nitrogen gas, is called denitrification. You got it? This process is called denitrification. Then nitrogen fixation is, again the gas is converted into ammonia. Ammonia will come to our body. So this is called nitrogen fixation, that will happen in plants, and then plant to organism body, it's called assimilation process. So the whole nitrogen cycle. So conversion of ammonia to nitrate is called nitrification. Nitrate is converted into nitrogen gas is called denitrification. Please remember this process. First, nitrogen removal by providing additional aerobic biological treatment. We already did a biological treatment, right? ASP by aeration. Still, we need a additional aerobic biological treatment for the removal of nitrogen from the wastewater. So here we have two-step nitrification process. First is nitrosomonas that converts ammonia into ammonium nitrate, and then nitrite converted into nitrate. As I mentioned, NH3 will be oxidized to O2 we are adding, it will be converted into NO2. Then after adding O2, it will be converted into NO3. Addition of more oxygen. So this process is called first is called nitrosomonas, that is one step. Then second step is called nitrobacter. I mean the bacteria involving in this is nitrosomonas. Second is nitrobacter. So a whole process is called nitrification. Okay, then this nitrate, this ammonia, nitrate, then this nitrate converted into nitrogen gas is called denitrification process. You got it? This is oxygen requirement. This is anoxic process. No requirement of oxygen. This denitrification process. But we need a additional organic source in this process for the additional carbon source for the denitrification process, because all of this process will require oxygen that will act as a electron acceptor. But here there is no oxygen. We need an additional carbon source to be act as a electron acceptor. Okay, so that need to be you can see in this equations. All this ammonia converted into nitrite, nitrite converted into nitrate. Here oxygen will be acting as an electron acceptor, or directly ammonia can be converted into nitrite. That is nitrifiers bacteria will also act upon. But denitrification, if you see, this nitrate will be converted into nitrogen gas, but where we will use any electron acceptor, we have to use some carbon sources like methanol, or any again wastewater if you add, that will act as a carbon source, or anything you can add as a carbon source to be used as a electron acceptor. So that facultative bacteria will act upon this carbon source using the oxygen bound with this, and then it will convert into nitrogen gas. CO2 will form and new bacteria cells will form. That is a denitrification process. See, wastewater they are using, methanol they are using, acetate they are using as a carbon source in the denitrification process. Okay. So for the effective nitrification to be happen, we need oxygen as well as alkalinity in your wastewater. We need oxygen, you know, right? Nitrification is a aerobic process. Also, we need alkalinity. Why? To maintain the pH. Because nitrifiers are the bacteria to convert ammonia to nitrate. So that nitrifiers require 4.5 milligram of oxygen and 7.14 milligram of alkalinity. Alkalinity, you all know what is alkalinity? Presence of hydroxide, carbonate ion, bicarbonate ions. So this will increase the pH of your system. So presence of carbonate, bicarbonate and hydroxide ion are called alkalinity. So we need a total of 7.14 milligram of alkalinity as CaCO3 in terms of CaCO3 we need. Okay. And for 1 milligram of nitrogen formed, and it will also yield 0.06 to 0.2 milligram of volatile suspended solids as a biomass or as a sludge per 1 milligram of nitrogen formed. Also, nitrification requires a longer retention time because we need to add more oxygen or for long time and low F/m ratio. Food should be very less, microorganism should be very high. It's indirect to the ASP process, and high means cell residence time, that is more time we need to provide with a reduced pH by maintaining the at this 7.14 milligram of alkalinity pH we can reach this nitrification process. See, again, BOD to nitrogen ratio should be greater than 5. Carbon dioxide nitrification may occur in a single reactor like ASP, RBC you can use. But if you want a separate or two-stage reactor, we can use BOD by TKN values less than 3 also we can maintain because it is very high nitrogen value. So we need a separate reactor. If we can use in a single reactor, if BOD by TKN value is greater than 5. So that can be done along with the secondary process. Then denitrification. Denitrification can be done in anaerobic system, that is facultative heterotrophic bacteria will act upon. So heterotrophic requires a carbon source like Pseudomonas, Micrococcus, Achromobacter and Bacillus are this facultative heterotrophic bacteria that can convert nitrate into nitrogen gas, or it will accumulate into the bacterial biomass and it will produce sludge. So here oxygen are depleted, nitrate becomes the primary electron acceptor here, but we need a organic carbon for energy, right? So there endogenous decay will happen. So what is endogenous decay? All the bacteria will eat upon its own protoplasm and it will form the sludge. So supplementary carbon sources such as methanol will be added. See here, separate system and a single stage system. In separate system, after ASP, we are doing nitrification process. But in single stage system, both BOD removal and nitrification will happen in a single tank. This requires after ASP secondary clarifier. After nitrification, we need nitrification clarifier. Because here, after primary clarifier, we can have only one aeration tank for longer retention time with less F/m ratio. We can use only one tank and one nitrification clarifier. But attached growth, if you see, we can use it as a single stage and two stages. So we can go after the ASP, we can go with this tower trickling filter or RSB, RCB, rotating by axial contractor, RBC. So here you can see anoxic process denitrification. So denitrification we are doing first. Why we are doing denitrification first? Because initially we have lots of wastewater as a carbon source. First we can do denitrification and then we can go with aerobic nitrification that can be given as a feed to the anoxic. So this is pre-anoxic denitrification stage. Post-anoxic is after nitrification we can do denitrification. That is common process. This is single stage and two stage. So based on where we are keeping the denitrification process and also based on we have two system or single stage system, we can divide the system accordingly. You got it? So this is the design criteria. Finally, a new technique called Anamox process. Here, ammonia converting to nitrite, then to nitrate. This is oxygen, nitrite, then to nitrogen gas without oxygen. Denitrification process, ammonia gas will be formed. Here I am directly mixing this two and forming nitrogen gas, skipping this process. So this process is called anamox process, anaerobic ammonia oxidation, anaerobic ammonia oxidation. That's called the anamox process. Why? How it's happening? See, ammonia, nitrite, nitrate, then nitrogen. We need oxygen, oxygen, and we need a carbon source. I'm directly converting this two into nitrogen. How? This will act as a oxygen source because we have O in NO2, and this will act as a carbon source, and we are doing the same denitrification process here. That is, without oxygen, this will act as a carbon source, this will act as the oxygen source for the electron acceptor, and it will go through the denitrification process and it will directly form the nitrogen gas. So this process is called anaerobic process. Anaerobic because we are not supplying oxygen, ammonia oxidation to nitrogen. So that's called anaerobic process. You got it? So that will be carried out by a bacteria called anaerobic bacteria, Candidatus Brachydia anamoxidans. That's the bacteria helping this anamox process. So very simple. Nitrogen we need to remove from the wastewater. We have different forms of nitrogen in our wastewater. Converting in by addition of oxygen or without oxygen plays a major role. Okay. What is the advantage of anamox process? Oxygen addition can be reduced because we are not adding any oxygen. Anamox bacteria is not required, requires organic carbon because this will act as organic carbon, and excess sludge will not be produced. CO2 emission will be reduced. But disadvantages is it requires high cost for construction and lots of knowledge required for the denitrification process. Here see the same in a different pictorial representation. Ammonia nitrate after adding and then it will convert into nitrogen gas. But here partial nitrogen nitrification will happen. Why? We need to convert ammonia to some into NO2. After partial degradation, both this ammonia and the partially converted nitrate will go to the anamox process and it will form the nitrogen gas. So we need a small partial nitrification process required to convert into NO2 because we need NH4 plus NO2, right, to convert into nitrogen gas, and new H2O will be formed. So this requires NO2. So this slightly nitrified to NO2, then it can follow this process. See, the same, this can be eliminated and directly we can go to anamox process. The reactor volume will be very small and the oxygen supply is not required, or small for partial degradation alone we need small quantity of oxygen. Chemical is not required. Sludge production will be very small, and also we have a carbon source requirement reduction. That is also you can add one point. Carbon requirement, additional carbon requirement is eliminated. Okay. Then optimum temperature, if you see, this is 10 to 37 for the nitrifiers and denitrifiers, but here 25 to 37 for the anamox bacteria. This all are about nitrogen biological treatment. Nitrogen chemical treatment, we are going with the ammonia stripping or air stripping. How it will work? See, uh, under proper controlled condition, air stripping can remove ammonia nitrogen by converting ammonia, which exists predominantly in unionized form at the high pH level. See, at high pH, ammonia will be in the form of nitrogen gas. So that is the principle behind this. Here, gaseous phase ammonia and aqueous phase ammonia exist together in equilibrium form. So we are forming liquid phase ammonia into gaseous phase ammonia that will be removed from the system. You got it? So that's the process behind this chemical conversion. NH4 plus in the liquid will be added with the alkalinity to make it into high pH, and we can form gaseous ammonia and water. It's not a nitrogen gas, it's a gaseous ammonia that can be evolved from the system. So transfer of ammonium from wastewater to air, that's called the air stripping. pH requirement is greater than 11, complete conversion of ammonia. So here we can add lime to increase the pH, to raise the pH and precipitate the alkalinity. Add excess OH ion for pH adjustment. Air to wastewater ratio should be 2000 to 6000 meter cube per meter cube of wastewater. And design criteria, you can take the depth of 7.5 meter and hydraulic loading rate as 40 to 46 liter per minute per meter square of tower area. And this is very less expensive than nitrification and denitrification process because only one tank is required. Only chemical lime need to be added that can reduce the pH. Simple process. See, here we are putting the liquid in. Through this liquid will go through packed bed is there. Air will be passed from here. So ammonia gas will be taken out along with the air and it will go out. Here in the packed bed lime will be there. So while passing through the lime, ammonia will be converted into ammonia gas. That's called the air stripping. Or here also you can do stacked. This is packed. This is tray type. So while passing through the tray itself, it will form. Okay. Now nitrogen is removed from the system. We have phosphorus. Both are nutrients, right? So phosphorus again we have two things. One is biological phosphorus treatment, another one is chemical physiochemical phosphorus treatment. Phosphorus will be in the range of 1 to 2 milligram after secondary treatment. We have three similar to nitrogen. We have three forms of phosphates: orthophosphate, polyphosphate, and organically bound phosphate. This can be removed chemical precipitation that is expensive and it will produce lots of sludge. So biological phosphate removal is another step. It will reproduce less sludge. Okay. So how to go with biological phosphorus method? Specific bacteria. There we have nitrosomonas nitrobacter, right? Like that we have polyphosphate heterotrophic bacteria. Polyphosphate heterotrophic bacteria. Please remember. So that is polyphosphate accumulating organism. PAOs we will say. Why it's called like that? It will accumulate phosphate in its body. More than 20% of their body masses will be accumulated with the phosphates under specific growth regimes. That's why they are called phosphate accumulating organisms or polyphosphate accumulating organisms. Some I have a work on biodiesel production. I have used yeast as culture. Oleaginous yeast is the one which will accumulate 60% of his body weight with the fat. So I can extract biodiesel from that fat. Similarly, this poly accumulating organism, phosphate accumulating organism will accumulate phosphate on its body, 20% of their bodies. So that kind of organisms we can use for biological treatment of phosphates. So here COD to phosphate ratio is greater than 45 we require. That means very less phosphate, I mean 50% of should be phosphate, higher phosphate levels. Release phosphorus from their cells and biomass enriched in this bacteria is separated so that phosphate level in the water will be decreased substantially. Biosolids, whatever the biosolid that is produced will have high fertilizer value. See the reaction here. After the influent will go through the anaerobic reactor. This again the phosphorus removal is also anaerobic process. So here after that it will go through aeration process. Then clarifier it will produce lots of sludge. That sludge will be the new biomass that can be having phosphate in its own body. So presence of sufficient volatile fatty acids in the anaerobic reactor. Upstreams will have an aerobic reactor triggers the PAO development. So we need to form the volatile fatty acid here. Then PAO reaction will happen here. Then new cells will be formed that will be settled here with phosphate. Then that can be recirculated again. How can we do enhanced biological phosphorus removal? That is EBPR. So here in this process, anaerobic environment only, the PAOs absorbs the volatile fatty acid in their cells such as polyhydroxybutyrate. So see here, polyhydroxybutyrate will absorb the volatile fatty acids in its body and it will use energy from the conversion of phosphate to polyphosphate. So that will be having the ATP, that is the energy source will be acquired here. So after this PHP will help in the formation of new cells and it will also during this formation also it will take the phosphate. So this is called enhanced biological phosphorus removal. This is anaerobic process and during aerobic process the produced BHP is used by the PAOs for the production of new cells, that is the regeneration of polyphosphate. Again it will absorb the phosphate in its body. So here two times the phosphate is accumulating in its body for the production of new cell biomass. So that's why we have both anaerobic system initially to produce the PHBs and then the aeration system. Here we are using the new cells produced by PAOs. right? So we can use mainstream process or the side stream process. On the mainstream itself, we can use the anaerobic and aerobic treatment, or we can use side stream process. Then after removing phosphate by biological treatment system, we can also think about the chemical method, but it will also produce lots of sludge. That is the major problem. So in chemical treatment system, we have two methods. One is lime addition, another one is alum addition. So how lime and alum addition will help in phosphate removal? Excess of lime is added, phosphorus will be precipitated as calcium hydroxide. Along with the calcium hydroxide, it will precipitate. See, calcium, phosphate, or OH ions will form hydroxy it's a calcium phosphate and OH combination. So this will get precipitated and flocculated and removed from system by settling. We have a settling tank. But the amount of lime required is not based on how much phosphate is there. It's based on how much alkalinity we need to provide. Because phosphate will precipitate as at a exact pH. So we need to maintain that pH. For that we are adding the lime CaO or CaOH twice. So hydroxide we are adding. So it's not based on how much phosphate is there. It's not based on how much pH we need to maintain. You got it? So pH of the water will be raised to 10 to 11. We can reduce the phosphate. Then again, second method is alum flocculation. We can add alum, aluminum sulfate. It will form aluminum phosphate as a precipitate. So here also it requires flocculation with the polymer and filtration to achieve adequate removal of the precipitated part. It will be pH range is 6 to 7 we can use, but lime will make it to 11 to 12. After removal, we need to again add acid to neutralize the water. So alum will mixed with the water, it will act as an acid, reducing the pH by reducing the alkalinity. So optimum phosphate removal is generally at 6 to 7. So we need to maintain that range 6 to 7. Right? Here see adsorption and ion exchange. Now we are done with the nutrient removal. So N and P are removed both with biological as well as with the chemical methods we have discussed. In nitrogen, okay. So now we are going with the adsorption and the ion exchange process. What's the difference between adsorption and ion exchange? First, what is called adsorption? See the diagram. Adsorbing and absorbing difference. Absorption is a material is there, whatever the pollutant in the water will be transferred into the adsorbent. Adsorbent is the material we are going to use to treat the water. So that adsorbent will absorb the particle on the body. That is called absorption. But if it is absorbing on the surface, then it is called adsorption. On the surface is adsorption, into the body is called absorption. But again taking out is called desorption, right? Surface is adsorption property, so it's a surface phenomena. Absorption is onto the body. Take an example: if you put sponge on water, it will absorb the whole water. That is called the absorption process. But similarly, if you put the sponge in sand, it will take the sand on its surface. That is called the adsorption process. Got it? So removing wide range of compound like micropollutant, non-degradable organic compound, and few metals can be removed with the adsorption process. So here the process is mass transfer. Accumulation of pollutant on the solid surface. Surface is a surface. It's a surface phenomena. So we have two steps in adsorption. First, the water will move along with the pollutant near the surface of the adsorbent. Adsorbent will be a circular or semicircular or any shape it will be. Right? We can make activated carbon from any waste. We can make activated carbon. It will have large pore size and more surface area. So this increase in the surface area is required for the absorption of the pollutant. So the pollutant along with the water will come near the adsorbent. That's the first step. Mass transfer from the water medium to the adsorbent phase medium. Then diffusion into the pores. It will move through the pores. That is second step. Third step is adsorption onto the surface of the adsorbent. So this is called adsorbent. This is called adsorbate. What is a pollutant? That is adsorbate. The material we are using to adsorb is called adsorbent. You got it? So movement of the pollutant from the water to the adsorbent medium is called the first step. Diffusion through the pores is the second step. Absorption onto the surface of the adsorbent is called the third step. Just movement of the pollutant coming in contact, diffusion through the pore, adsorption onto the surface. This is a simple 3 steps. So we can classify the adsorption based on physical and chemical process. So physical will be weak bond van der Waals force. Both adsorption is exothermic process, but physical is reversible. We can wash and take out. But chemical adsorption is irreversible. With the proper chemical bond, it will form. Okay. Exothermic process will release energy, as you know. Both absorption will release energy like in the form of heat. Physical absorption will produce zero point 0.1 kilocalories per mole, but chemical absorption will produce 10 kilocalories per mole. Mainly used adsorbent is activated carbon. Other adsorbent like zeolite, clay mineral, silica gel, silicic acid can also be used, but mostly used is activated carbon. Activated carbon again classified into carbon black, nanotubes, graphene. Nowadays, most of the researchers are working on carbon nanotubes, very fine nanotubes in the range of it's in already in the name mentions it's in the nano, 1 nanometer, 2 nanometer dia. It's not, I'm not saying the length, I'm saying about the dia. So it will be that much micro nano level. This carbon can be used in all medical applications, semiconductor applications, now water treatment also we are using. So lots of applications are there for carbon nanotubes. Those who are working on research, you can think about carbon nanotubes. And graphene, graphene is again working in lots of things like in military purpose because it's having a good strength in graphenes that can be used in water treatment also. Then the activated carbon can be in the form of 3 ranges based on the size: powdered activated carbon, granular activated carbon, extruded activated carbon. This is the extruded one. So it's in the range of 1 to 150 micrometer, 0.5 to 4 millimeter, and 0.8 to 4 millimeter. That's the size. So if you powder it, it's a powdered. If you are making a granule, that's a granule. And see the absorption on activated carbon. Numerous pores are required with a larger surface area. So whenever you are making a activated carbon from any waste, you can measure the surface area with the BET process. You can give for BET test, you will get the surface area. So you all know, right? Surface area. If it is a single circle, it will have only this much surface area. But if a circle with the pore, then we can increase the surface area from here to here to here to here. It will be more circumference, right? And this, if the pore extends, more pore, then more surface area, so more space for the pollutant to attach. Then after water treatment, we can take this carbon and we can dispose. That's the principle. So high degree of porosity, contaminant adheres to the surface of the carbon granules and trapped in the pores. It can efficiently remove organic metals, chlorine, fluorine, radons, even radioactive particles, and micropollutants like microplastic can also be absorbed on the activated carbon. But it is not effective with the microbial contamination. That's why we are going with the disinfection process, right? So activated carbon filters, you can see this the design criteria. And another one is we can do backwashing also. So raw water we are putting in, activated carbon is here, it will absorb, filter water will come out. Backwashing we can do for, because whenever you are putting water pressure, it will compress. So to loosen it, we are doing backwashing, it will loosen the carbon. After that, we are doing sterilization of stripping with the steam water. So that will sterilize and desorb the material. For particular pollutant, we have a particular chemical solutions that can be used.
Hello, sir.
Yeah, yeah, yeah.
Sir, when we have to carry out the backwash, is it to be carried out for every operations or at the end of the or at the 15 days? When
Yeah,
we have to
it's
carry
based
what?
on the head loss. So we have a proper head loss. This much quantity is required for this much time. That flow, whenever the flow is less than the critical flow, then we have to do the loosening stage. Also, when the quality not matches, we have to do the stripping process. So whenever the pack is fully tightened, the flow will be reduced. So that can be calculated. Whenever the flow is less than the critical flow, then you have to loosen the thing. So we need to do backwashing. And also, whenever the quality you are putting 100 milligram of a pollutant, we need 10 milligram. But after some time, the carbon got exhausted, and you will get 20 or 25 milligram of effluent. So that need to be taken care. So we have to stop the process. We can do the stripping method that will take away all the pollutant on the carbon, and the carbon will be purified. So that's based on the head loss and the effluent quantity. So based on that, you can calculate the time also. Usually within a week like that, they will do. But that's for water treatment we can do. But for wastewater, you have to calculate the days and it will be done accordingly. Hope you are clear. Let me move on. So activated carbons are effective for most of the pesticides. Lots of pesticides are listed. Mostly 95 to 99% we can remove this type of pesticides. Phenols, alcohols, color compounds like dyes we can remove. Right? Dye is again an organic compound that can be removed. So second process is ion exchange. Ion exchange is only used for dissolved inorganic compounds. Ionic impurities like chlorides, sodium.
Sir, activated carbon effective in the case of acids?
Effective for acids.
Yes, sir, acids.
Acid treatment you are saying.
Yes, sir, acid treatment. If the water is polluted with the acid, and
No,
then
no,
we
no. Acid is a like it's with the H plus ion. H plus ion cannot be removed with activated carbon. You can simply, why we need activated carbon? Simply add alcohols. OH ion you can add, it will be treated. What is the issue? Why we need activated carbon? Yeah. Simply you change the pH by adding alkalis like any OH or something.
okay, sir.
Yeah. So pH adjustment we can do simply. That cannot be done with activated carbon. Yeah. So ion exchange will remove this type of ions, inorganic ions, dissolved ions. So and also hardness causing agents like Ca2 plus, Mg2 plus kind of things can be removed. So here the principle is we have a polymer backbone with a functional group that can attach a compound. This element will be replaced with our pollutant. Chlorine will go here. This will be released into the water. Similarly, calcium will go here. The functional group will release that one. It's based on the reactivity of our pollutant with the functional group. So the already adhered substance will have less reactivity, so it will come out. Our pollutant will have more reactivity, so it will get absorbed. You got the point? So it's the exchange with another non-objectionable, because this compound should be non-objectionable, that will come out with our water, and it will be less objectionable ionic substances like sodium or any less objectionable compound need to be given to our water, and like H plus can also be released. Then our pollutant can be adhered. Alright. This is a physical chemical process that will be swapped between solution phase and the solid resin phase. From the solution, our pollutant is going. From the solid phase, that non-objectionable ion is coming out into our water. It's an elastic three-dimensional hydrocarbon network having electrostatically bound to the resin. So electrostatic bounding is a physical sorption only. So target ion, whatever my pollutant is, accomplished by continuous passing of water, one or more column packed with exchange resins. So whenever it's passing through, it will absorb. Hold the retained ion temporarily and then release it by regeneration. Similar to absorption, it will hold the pollutant. Whenever we are doing backwashing, it will release the pollutant. So how can we fix the resins? The resins is the one which will do the ion exchange process. So that resins are strong acid cations, strong base cations, weak acid cations, weak base cations. So it's based on the functional capabilities of the resins. See here, the strong acid will have, resins always have a zeolite or any Z compound. You can replace with the silica, you can replace with the sodium silicate, Na2H6 something. You can do any resins, you can combine with the acid, that's the strong acid cationic resins. Similarly, strong as weak acid cationic resins that will be having a COO bond, this is a sulfate bond, and the strong base cation OH will be there, weak base cations are there. So based on our target pollutant, if you are treating the hardness, we can go with the acid cations. If you are treating chlorines kind of things, we can go with the base anions. You got it? What are the pollutant you can remove? See here, all the cations can be removed. So that's why we are using acid cations, because that cation will come to your water. My water will have all the sulfates chloride, HCl will be formed, H2CO3. So this is non-objectionable. Only the pH will get reduced. I can easily adjust again with the addition of any increase with NaOH. I can add to remove this pH, to adjust this pH. But my calcium and magnesium will be attached with the resin. So I have removed from the water system. You got it? So that exchange is happening between, that's why it's called ion exchange resins. Ions are getting exchanged. So these are all ion exchange resins. We have cation, organic resins, ionic resins, organic synthetic resins, everything you can check based on the pollutant, target pollutant you are going to think. What is the principle behind this? Principle of selectivity, as I mentioned. If you have copper and mercury, first copper will go and attach fast. If mercury is there, mercury will come out, copper will go there. Similarly, if you have magnesium and calcium, magnesium it is attached, it will come out, calcium will go, because calcium is having more selectivity. So based on the selectivity of the resins, it will go and exchange. You got it? Yeah. So anion demineralizes, cation demineralizes. Demineralizes are, it will whatever the minerals are there, that will come to the resin. The water will be demineralized and mixed bed also there. Typical process is simply zeolite resin will keep. So ion exchange. Some resins will have ZH plus, that will replace H plus, and Ca plus will be attached with this. So H plus will be taken out. Second combined resin, it will pass through ZOH. OH will be coming to the water, so H2O will form. My other Cl minus will be attached with this. So C and Cl will be removed from the system. H2O will be formed in the system. You got it? So cation will be removed, anion will be removed. So both cation and anion are mixed in this kind of mixed bed demineralizers. So how can we do the regeneration? Similar to activated carbon absorption and ion exchange process, we need a regeneration. That is, whenever the ion got exhausted with the pollutant, we can do regeneration with these solutions that can wash out the pollutant from the resins, and the resin will be regenerated. We can do backwashing, we can do regeneration chemicals. Like if chlorine are more in the resin, again for chlorine removal, we can simply make a chemical to remove the chlorine with Na solution, that will form NaCl, and it will come out with some 10 liters or 20 liters as a drain solution that can be treated separately. You got it? Then rinsing with the trace, last trace of regenerated chemicals. Also, we need duplicates of this type of reactors. One should be in function, other need to be regenerated. After this, it will be in function, it will be regenerated. So we need at least duplicates so that we can operate at the same time. The same quantity of water that is coming can be like shifted to the reactors, shifted between the reactors. See, how can we regenerate? Can we regenerate it from the same side or from the back side? Once the resin is clear, our pollutant is coming and attaching, it will exhaust the resin. But if you are doing regeneration from the same side, from top to bottom, see, clearing, but some pollutant is attached still to the resin. After again, if you start, that pollutant will come out with the pure water, right? So the problem is, you are doing regeneration from the same side. So whenever the exhaustion is happening from this side, regeneration should be done from the back side, so that the pollutant resin will be completely regenerated from bottom to top. You can do the alternative also. Exhaustion can be done from bottom to top and regeneration from top to bottom, but it should be reversed. That's called concurrent and counter current. Concurrent, if you do, some pollutant will remain in the system, but counter current, if you do, you can get there only, it will not leach out. You got the principle behind regeneration. So that's what. But the ion exchange have some limitations, like exhaustion will be the problem, differential pressure. We need to apply lots of pressure and temperature, radiation exposure, and competitive ions. Because see, as I mentioned, the ions list, some will have similar selectivity. So that competition will happen between ions. So that's one of the limitation with the ion exchange process. So we have finished the nutrient removal. We have thought about the absorption, ion exchange completed. Then now we are going with the membranes. Membranes, AOP and disinfection is pending. So membranes, you all know, simply we are filtering the water. That's the membrane. We all have RO in our households. So water is having pollutant that will be passed through the membrane at high pressure. So that will give you the clear water. Whatever the pore size, less than that only it will come out, right? So that's called the solute particle and solvent particles. So we have four types of membranes: microfilters, ultrafilters, nanofilters, and reverse osmosis. Microfilter will remove all the bacteria. Ultrafilter will remove macromolecules. Nanofilter will remove divalent ions. And RO removes monovalent ions, and only water will come out with the RO. That's why we are using RO for drinking water systems. But wastewater treatment, we can think about any of these two filters. If you have a good quantity of money, you can think about nanofilters also. Nano is the size of the opening. Okay. So membrane process, it's a selective barrier, combination of sieving and diffusion process. So sieving is trapping, diffusion is the water that is coming out. So both will happen over a wide range of size, selection, and molecular weight. So if a bigger particle will have huge molecular weight, so it will trap. So pure production of pure water is the aim. Seawater to freshwater also we can think about RO, but it will they have problem with the life expectancy. So expensive, but if you increase the life expectancy, it will become less cheaper. Okay, so tubular membrane will make the water through flow through, and clear water will come out. That is a permeate, and reject or concentrate will have more pollutant in it. So if you pass 100 liter, 75 liter will be pure water. 25 liter will have all the contaminant present in it, right? That will be again a problem. How to treat that? 25% is a problem. So we have a evaporator, multiple effect evaporators, MEE, that can we do, so that water will be evaporated, salt will be remaining, that salt we can dispose, right? So if you go to any distillation seawater treatment process, you can go and see this type of multiple effect evaporators. So membrane can be classified based on driving force. Which will be the driving force? If I am applying pressure, that is pressure driven operation, micro, ultra, nano, reverse osmosis, and all work on that. Concentration driven. So like dialysis, more concentration is here, less concentration is here, which will go. So that's a dialysis per evaporation. Per evaporation, forward osmosis, and artificial lungs and gas separation process are concentration driven. Even most of the medical treatments are also working on this type of membrane, because our body will purify the blood based on this type of systems only, right? And electric potential gradient. So based on electric potential, we can classify as electrodialysis, membrane electrodialysis, and electrofiltration, fuel cells. Temperature gradient, membrane distillation. One of our research team is working on membrane distillation. So membrane will be there, hot water, cold water will be there. That temperature gradient will make the water to flow through the membrane, right? That is a temperature gradient. Gradient is slope or difference. So high temperature, low temperature, that will make the water to flow. High pressure, low pressure, it will make the water to flow. That is pressure gradient. So if you see the spectrum, microfilter will remove all this, nanofilter will remove all this. Like that, you can see what are the target pollutant that can be removed. Microfilter, nanofilter, reverse osmosis will remove all this, and they will give the pure water. See, micro and ultra will be pure staining, pressure is used. Nanofilter will remove divalent cations and anions, but having molecular weight greater than 150, 500 will be removed. But pressure record is lower than RO. There is an osmotic pressure developed. What is osmotic pressure? Whenever there is a system having a membrane, higher concentration and lower concentration, the water will move from high concentration to low concentration. But water will move from low concentration to high concentration. That is called the osmosis. But I need from here to here, that is called reverse osmosis, right? So I will apply some pressure here. So to counteract the osmotic pressure, I am giving a pressure that is reverse osmotic pressure. So nanofiltration, there will be a osmotic pressure problem. But reverse osmosis, I am giving a reverse pressure to the osmotic flow. Membrane high pressure side, producing highest quality permeate. and least amount of waste. Here 95% can be removed, particulates and dissolved salts. That's the major one. Dissolved salts can be removed if we are using in the drinking water. Again, we are adding copper and things and all before drinking. So we need minerals in our water. So we can do dead end type and cross flow type. Dead end type is this type of vertical flow. Permeate will be permeate will be passed and concentrate will stay here. But here, if you pass horizontally, good water will pure water will come out. Permeate will reject will be taken care of here. So water treatment system will happen here. But here all the pollutant will accumulate here itself. That's a dead end and cross flow type. Based on structure, we can classify as plate, frame, large tube, spiral wound, hollow, fine tube. You can see the picture. So the water will feed into this membranes. In between the membranes, the gaps, and it will filter through the membrane sheets, and through this net, it will pass through, and the permeate will come out. And the other between the membranes, this concentrate will come out on the other end. You got it? Similarly, hollow fiber tube also. Between the hollow tubes, we have the feed, and permeate will come out from this. It's a cross flow section. So pure water will come out and the concentrated water will go out. Similarly, tubular structure, the similar to hollow fiber, only one structure. You have a tube kind of thing. So permeate will come out and the concentrate will be flowing in this direction. So actual industrial scale, it will be like this. It will have a stacks of tubes. Inside each tube, we have a different sheets. In each sheet, we have different membranes. So it's a collection and the tube structure. You can see here. So what are the type of material you can use for RO, polysulfonate material, polyalkylate material, like that? But the application is maximum for salt removal and hardness removal. We can also use for heavy metal removal, color removal, and microbial contamination removal. So RO will remove microorganisms also. Electrodialysis is the other process. It will be electric driven, electropotential driven. It will also remove the dissolved ions. Ions move from current direction. See, I will explain with the picture. We have two high potential electrodes, anode and cathode. So water will be passed through this. The secondary treated water will pass through this. Okay, we are leaving one in between. The anions are minus, right? Anions will pass towards cathodes. So anions will pass towards cathodes. We have alternate cathode membrane, anode membrane, cathode membrane, anode membrane. So this anions will pass through the anode membrane and will move towards the anodes. But here we have a cathodic membrane that will again counteract the same ion and it will trap here itself. Similarly, anion will pass through cathode through the cationic membrane, but again an anionic membrane, so it will trap here the ions. So all the ions are trapped in between. It will be taken as a concentrate. Pure water will go through this. You got it? You got the system? So the ions will move between one membrane. It will be trapped because of the potential and it will be taken out. We have membrane, we have electrode, we have a potential difference. It will treat the water. That's called the electrodialysis. So membrane fouling is the problem. We have a membrane. All the pores will get clogged. That's called the fouling of the membrane. We can't get the exact quantity of water or quality of water. So how to counteract the fouling? Chemical fouling and biological fouling will happen because the salt will be accumulated on the pores, or the microorganism may attach to the pores and it will grow. So that's membrane chemical fouling and biological fouling. How to control the fouling? By prefiltration, chlorination, and UV application. So this will kill the microorganism and it will clear the membrane. So to counteract the membrane fouling is a major research problem. Again, so membrane cleaning, we can do physical, biological, and chemical treatments like sponge, water jet, and backwashing systems, or a disinfectant we can use. So also concentrate whatever the material we are getting out, that's concentrated solution. How can we dispose in that? In the deep well injection, evaporation we can do. That is what we can do, because zero DQ discharge will be evaporation only. We can't do deep well injection, that will again pollute the groundwater. So evaporation will be the good thing. At saline wetland we can use. You can also think about wetlands is nowadays increasing research area, but saline wetlands you can think about a good research problem. So membrane advantages, high performance, good removal, even microorganism also it will remove. But the disadvantage is membrane fouling and the reject treatment, because we are producing a reject that is having huge problem. Finally, solids removal. Again, this is a simple topic of solids will be removed by sedimentation, filtration, or coagulation. So, by adding alum, lime, or iron salt as a chemical, smaller particle can clump into flocks, similar to the water treatment. In water treatment, also we will use alum as a flocculating agent or a coagulant that will be mixed thoroughly with the water with the flash mixture, and slow mixing will form the flocks, and then the sedimentation will remove the formed flocks. That's a coagulation flocculation treatment for solids removal. The same we can use for solid removal in wastewater also. Organic coagulants and inorganic coagulants we can use. That's called the chemical co-precipitation method. So here we are adding a suitable chemical to maintain the pH. At a particular pH, all this heavy metals will precipitate. See, copper will precipitate at 9. Nickel will precipitate at 10.5. Cadmium will precipitate at 11. Lead will precipitate at 9.5. Zinc will precipitate at 9.2. So I can maintain the pH of the water at this range, so that all the metals, heavy metals, will get precipitated in the flocks, and the flocks can be removed, right? So we have to raise the pH to a level, target level, for the target metal to get precipitated as metal hydroxides like copper, nickel, and iron. So arsenic get attached to the flocks through adsorption. That is called co-precipitation, because we are doing alum. That alum will form the flock. Also, this precipitate will attach to that flock. Flocks will have a gel, sticky precipitate. So that will help in sticking. So that will form a coagulant kind of thing, alum iron salt coagulation. So that will be co-precipitation process. We are doing precipitation as well as the flocculation. So coagulation flocculation process, many microparticles and charged ions are attached onto the flocks. Finally, advanced oxidation process. It's the major research work our team is working on. Maybe you can think about the profile of Dr. R. Gandhimathi in NIT Trichy. Madam is working fully on advanced oxidation process like sulfate radical based Fenton process and electrofenton process. So what is called advanced oxidation process? All the organics need to be fully converted into CO2 and H2O without any byproduct. That's called advanced oxidation process with the help of hydroxyl radicals. It's not OH minus, it's OH dot. Hydroxyl radicals is the one radical will produce from different sources that will completely mineralize the organic into carbon dioxide into water and some inorganic compounds. That's called advanced oxidation process. We can use advanced oxidation process as a pre-treatment, because our biological system, what we have discussed this much time, cannot work with the recalcitrant pollutants or highly non-biodegradable pollutants. So some non-biodegradable pollutant may be used with the AOP to break the bond, and it will form a simple compound that can be easily treated with a biological treatment process. So AOP can be used as a pre-treatment process with the help of hydroxyl radical, that is highly reactive hydroxyl radical that will oxidize the organic matter into simpler compounds. So we can produce the OH radical from photochemical degradation, photocatalysis, and chemical oxidation process. In photochemical, we can use UV with ozone, UV with H2O2. H2O2 is the major hydroxyl radical producer. Or photocatalysis, we can use TiO2 as a catalyst, or UV as a catalyst, or phenton as a catalyst to produce the OH radicals. Similarly, oxidation process, we can use ozone as a OH radical producer along with the H2O2 as an oxidation process. So AOP will use OH radical plus the pollutant will form the fully mineralized compound. So homogeneous process, heterogeneous process. Homogeneous will use only one UV as a catalyst and O3, H2O2 and UV, or this type of similar things. But heterogeneous will use both energy, with energy and without energy. Without energy we have chemicals alone. With energy we have UV, US is ultrasound, that and all. If you use both, that is a heterogeneous process, like catalytic oxidation, photochemical catalytic oxidation, heterogeneous photocatalytic oxidation. So first, AOP will oxidize the agents, and the toxic pollutant will be biodegradable compounds it will produce. That biodegradable compound can again use the oxidative agent to form H2O2 and water. The first AOP will form oxidative agent like OH dot. Then the OH dot will react with the toxic element like whatever the pollutant, dye or any pollutant I can, only organic pollutants. So that will be biodegradable. Again, the OH radical will act upon the biodegradable, it will form the water. Or you can skip this process, you can use this biodegradable compound and go with the biological treatment like ASP or something. Right, so it can destroy toxic organic compound, very efficient water disinfectant also, because microorganism is also organic, right? So it will also remove with the AOP process, cheap to install, adaptable to small scale. But the disadvantage is highly operational cost, because all the chemicals are costly, H2O2, UV, this kind of things are costly. It will form some intermediate product that is more toxic than the original product, so that also need to be taken care. Engineers are required, lots of research. It's still emerging area, AOP is still emerging, so we need lots of research on that. Finally, disinfection for the removal of microorganism. We have lots of disinfectant. Major one is chlorine gas, or OCl is the major thing that can be used. Hypochlorous acid, chloramines, ozone, UV can be used as a disinfectant. So that will remove all the microbes in your water sample, injected in the chlorination solution. So chlorine contact basin, we have a chlorine contact basin, water will flow. So at a different point we can add the chlorine like a plug flow, or you can add here itself, it will form a plug flow kind of thing. But it will be minimum of 30 minutes of contact time before supply or before disposal. So it's based on pH, contact time, organic content, and effluent temperature. If your organic content is more, then chlorination will not work, because chlorine will oxidize your organic compound. It will not be used for microorganism oxidation. So I need to remove all the organics before putting chlorine in my water sample. So see, this is a chlorination tank. This is a UV tank. Both you can use as a, but UV will also not work with the organics. Organics should be removed, or solids should be removed. Otherwise, UV light will not pass. That's why turbidity we have discussed in the first class. Turbidity, if it is there, UV will not work. So turbidity need to be removed fully before disinfectant with the UV. You got it? So we have discussed the tertiary treatment, advanced treatment for the removal of nutrients, nitrogen and phosphorus. Also removal of organics by AOP. For the removal of microorganism by disinfection. For the removal of dissolved organic matter, or TDS, by ion exchange and membranes. And adsorption is also for organic pollutants. You got it? So this is what we have discussed fully today. Nitrogen can be removed by biological as well as chemical. Phosphorus can be removed by biological as well as chemical. Nitrogen can be converted into nitrite and nitrate by nitrification, and into nitrogen gas by denitrification process. Also, we can skip the process by anammox process. Also, we can add chemicals like in phosphorus, we can add alum and lime as a chemical treatment. Biological treatment, we can use polyphosphate accumulating organisms, PAOs. So if you have any doubt, you can unmute and you can ask, or you can post in the chat box. Otherwise, we will move on to the problem solving session. So please read once. It will be very easy if you read once. This is the whole idea we have discussed today. Can I move to the problem solving session? Okay. Okay. So let me read the question. Please post the answer in the chat box. Which of the following contaminant require advanced treatment of wastewater for their intended removal? Emerging contaminants, heavy metals, recalcitrant organic compounds, all the above. Please post the answer in the chat box, A, B, C, D kind of. Which of the following contaminant require advanced treatment of wastewater for their intended removal? Emerging contaminants, let me take the pen. Emerging contaminants like pharma, personal care products, kind of things can be requires advanced oxidation or advanced treatment. Heavy metal requires advanced treatment. Recalcitrant organic pollutant requires advanced treatment. So all the above is correct. Option D is correct. See, nutrients, finely suspended salt particles, recalcitrant organic pollutant, emerging contaminants, dissolved heavy metals, and resistant microorganisms requires advanced treatment or tertiary treatment. Second question. If you have any confusion, please ask me. Let me move on to the second question. In wastewater, alum flocculation or lime-based precipitation may be used to remove ammonia, phosphorus, refractory organic, salinity. So alum and lime are the two chemicals used to remove the nutrient nitrogen and phosphorus. So both have biological as well as chemical treatment methods. So this biological treatment are called biological nutrient removal method, BNR. Here chemical we will use alum and lime based. That's why it's called alum flocculation, and lime is used to remove phosphorus. Phosphorus is correct, right? See, lime based precipitation of phosphorus, alum flocculation for phosphorus removal. Both are chemical methods. Can you match this? First is the type of conversion, second is the name of the reaction. Sorry, name of the reaction with the type of the conversion. Nitrification. So we have, let me write first. Ammonia or organic nitrogen will be the major type of nitrogen in the wastewater. So first it will be oxidized to nitrite, then it will be oxidized to nitrate, then it will be reduced to nitrogen gas. So there is no oxygen here. So this process is called the nitrification process. Conversion of ammonia to nitrate. Nitrate to nitrogen gas is denitrification process. Ammonia to nitrogen gas is called mineralization process or fixation process. Organic nitrogen to ammonia nitrogen. Not this. So this organic nitrogen to this one is called a mineralization process. Can you match now? C. Nitrification is conversion of ammonia to nitrate via nitrite. So this is correct. Yeah, C is correct. Then denitrification, conversion of nitrate to nitrogen gas. This is also correct. A. Okay. Then mineralization is conversion of organic to ammonia. This is called a mineralization process. How the organic nitrogen will form? From nitrogen to ammonia by fixation. Then this will be assimilated. The back process of mineralization is called assimilation process. So our nitrogen will be taken as ammonia by the plants. In the plant we will eat and we will accumulate in our body as assimilation. Okay. So this is the whole process: mineralization, assimilation, nitrification, denitrification. Removal spectrum of ultra filter. We have microfilter, ultrafilter, nanofilter, reverse osmosis. Now you tell which is better. This is the range: micro, ultra, nano, reverse osmosis. Ultrafilter is in the spectrum of micro, ultra, nano, reverse. So ultrafilter will be between micro and the nano. So better than micro. No, better than micro, but less than nano. So this is nano and RO. I think B is correct. Right? Yes. Better than micro, but less than nano and RO. Remember microfilter, ultrafilter, nanofilter, RO. That's the range. See? Based on the size also. Size of the pores. Okay. The most commonly used adsorbent. During adsorption process, what is the most common adsorbent we will use? Alum, sand, activated carbon, natural clay mineral. Which one is most common? Activated carbon. Yeah, that is correct. That's why Coconut based activated carbon is more famous. That's why coconut shells are having lots of demand for the production of activated carbon is working with lots of skincare, face wash, even for absorption of more medicinal products. Everything we are using activated carbon, like carbon based face washes are nowadays available, like carbon black. So that and all using CHARS, activated carbon. This is the most commonly used adsorbent. Ion exchange system operating downflow. Ion exchange system, we have lots of ion exchange membranes up, operating downflow. Okay, in normal service run. Upflow regeneration. Regeneration we are doing upward. Why is preferred over downflow? Because reverse flow regeneration prevents ion leakage. Right? This is correct. Upflow regeneration is expensive. No. Upflow generation requires much less time. No. Because whatever the membrane we are first using from top to bottom will accumulate all the pollutant here, but after we are doing the same regeneration it will clear only up to here, it will not clear the full. But if we start regenerating from bottom to top, it will first clear all this and only small thing will be here that will not come out in the next step, right? So reverse flow regeneration prevents ion leakage, so this ion leakage will be prevented. See, after treatment also we have some leftover. That is the problem. So counter current we need to do. Which of the following treatment process is used for mineralization of organic compound? Mineralization. Adsorption and ion exchange, it will not mineralize. Anamox process, it will produce N2 gas only. Electrodialysis, it will also remove some of the ions. Advanced oxidation process, it will remove organics plus OH radical will produce CO2 plus H2O. CO2 H2O is the fully mineralized compound, right? Plus some inorganics. So advanced oxidation process is correct. See, complete mineralization. Wherever you find complete mineralization, you think about AOP process. Ultrafiltration. Concentration driven, temperature driven, pressure driven, electropotential driven. So we have membranes differentiated based on driving force. If it is pressure driven, we have membrane filter, ultra filter, nano filter, RO. If it is pressure driven, so the answer is pressure driven for ultra filter. If it is concentration driven, dialysis and all. Electropotential driven, electrodialysis we have seen, right? Temperature driven, membrane distillation. So based on the driving force, you please remember the treatment systems. Identify the correct statement. In adsorption, pollutant transfer from fluid phase and get adhered to the solid surface, while in ion exchange, pollutant in water is swapped with another ion of similar charge held electrostatically on the surface of the resin. Both are correct, right? In adsorption, pollutant will come and adhere to the surface of the adsorbent. So this is correct. In ion exchange, we have a functional group attached to that, a non-objectionable non-objectionable same charge ion that will be replaced with our pollutant. So this is also correct. It is held at electrostatically, so weaker bond, so it will go out. So selectivity of my pollutant is more, so it will come. First statement is correct. Second statement, adsorption as well as ion exchange are only effective for removal of ionic compound. Ion exchange is used for ionic compound, but adsorption is not only for ion. It's not only for ion. It can be used for organics, dyes, ions, heavy metals, anything we can remove with the adsorption process. So, statement 1 is correct, statement 2 is incorrect. See, adsorption can be wide range of compound like micropollutant, non-degradable organic, few metals. But ion exchange can remove only dissolved organics, dissolved ionic impurities and have hardness. You got it? So second statement is wrong. Next. Addition of ozone to treat the wastewater provides. Ozone we can use in two treatment steps. One is in AOP as an oxidant. One is in disinfection as a disinfectant. So it will also advanced oxidation and disinfection, both it can do with the ozone. Answer is D. Addition of ozone. See, in AOP we have three type, right? Photochemical, photocatalytic, chemical oxidation. In chemical oxidation, you can see the ozone here, ozone with any other things. So it can mineralize. Similarly, because ozone is a good oxidative agent. Similarly, ground level ozone is harmful as per air pollution. Ozone in the stratosphere is good. Ground level ozone is very harmful because it will oxidize. So in the treatment plant we are producing, it will have a nanosecond of lifetime and it will die. Disinfection also we are using ozone. So both it will helpful. See, there is a problem. Can you attempt the problem here? It's very easy. Adsorbent column. Okay, we have an adsorbent column. Right? We have a packed column. 8 kg of granular activated carbon. Okay. What we are treating? 12 kiloliter of secondary treated wastewater in each cycle before being regenerated. Okay. The treatment is able to reduce the pollutant is PAH, polyaromatic hydrocarbon, from initially 40 milligram per liter to outlet is 6 milligram per liter. Please draw the diagram, then you will be easily understand. 12 kiloliter of wastewater is coming, 40 milligram we are treating to 6 milligram any pollutant. The concentration of PAH, that is a pollutant, on GAC after end of the cycle, how much it will be in the GAC they are asking. So think about how much is removed. 40 milligram to 6 milligram it has removed. So how much removal? 40 minus 60, 34 milligram of pollutant removed per liter. I have 12 kiloliter. So totally how much milligram I have produced into 10 power 3, you can delete this kilo. So 34 into 12 into 10 power 3, for 4 lakh 8,000 milligram of pollutant I have removed with 8 kg of granular activated carbon. So 8 into 10 power 6 milligram of activated carbon. So divided by 8 into 10 power 6. So I will get 1, 2, 3, 51 milligram per gram, or convert it into gram, 10 power 3. So take this 2. It will get 51. Are you getting 51? Yeah, I am getting. Yeah. 51 milligram of pollutant per gram of activated carbon. So after one cycle, after putting all the 12 kiloliter, if you take the granular activated carbon out, you will have 1 gram of activated carbon, will have 51 gram of pollutant in it. So how to dispose this? That also you need to think about. Okay. So answer 51 is correct. See, that is the answer. See this problem, RO membrane for advanced treatment. So we have a RO membrane. Always draw RO in. This is a representation for RO. Okay. Reduce the TDS. TDS is dissolved solids. Inlet is 1600 milligram per liter is given to the RO. It is reduced to 280 milligram per liter. That is the pure water. Okay. I have a reject. Okay. Now, permeate is the pure water. Reject is the concentrate. Okay. Clear about the name. 45% is permeate. So 100% water is coming. That is 1000 liter or 2000 liter. You can take any value. 100%. 45% is pure water. That is the permeate. So how much will be my concentrate or reject? 65%. Sorry, 55%. They are asking the TDS in RO reject would be. What is the TDS for this? So I can do the mass balance. Mass balance is, what is the inlet to outlet? One inlet. So mass balance is 1600, 100% 1600. Let me write clearly. 100% 1600 is inlet, mass in equal to mass out. All the mass out summation. That is the formula. Mass in equal to mass out. That's the mass balance. This is the mass in. What is the mass out? 45% la 280 plus 55% la I don't know what is the value x. Can you solve this? 100 into 1600 minus, it will come this side, right? 45 into 280 then divided by 55. I'll get 2680. Are you getting 2680? Simple mass balance. Total mass in, total mass out. 1600 milligram per liter of 100% is the mass in. 45% plus 55% is my mass out. Always it will be equal. Okay, answer is 2680. So very simple mass balance you can do. Any RO problem, you can do the mass balance. So now you see the inlet is having 1600, the pure water is having only 280, but the 55% of the outlet is having 2680 milligram per liter of TDS. That is very high, right? But if you see 95% treatment, 95% will come out and 5% is the reject, means it will be around 10,000 or 20,000 milligram per liter or 1 lakh even. That much of salt concentration, you have to think where to dispose. If you dispose in the ocean again, there won't be any life, aquatic life near that area of disposal. That's the problem with the RO reject disposal. That also you can think about. And after this membrane, what we can do, the foul in the membrane, that membrane solid waste also we need to think about. So rather research area you can focus on. This is the answer. Now this problem, if you see, nitrogen removal is treating 2.5 mld industrial water. So a nitrogen removal system. This is the nitrogen removal system. 2.5 million liter. The given quantity is 2.5 million liter. So 10 power 6 liter per day. 30 milligram per liter of ammonia. Alkalinity is 240 milligram per liter. So the inlet is having 30 milligram per liter of ammonia, NH3N, and 240 milligram per liter of alkalinity. As I mentioned, the nitrification to happen, we need a required alkalinity. So they given ammonia to be converted into nitrite or nitrate. 7.14 milligram of alkalinity is required, and it will produce 0.15 milligram of sludge per 1 milligram of nitrate formed. Based on the question given, the following requirement is additional dose of alkalinity needed. They are asking you need 7.14 milligram alkalinity per milligram of ammonia. What is the additional dosage of alkalinity required? See, we have 30 milligram per liter of ammonia. 1 milligram of ammonia requires 7.14 milligram of alkalinity. So 7.14, if you multiply, how much you will get? 30 into 7.14, you will get 214.2 milligram per liter of alkalinity is required. But already our system have 240 milligram of alkalinity in our wastewater. So what is the additional dose of alkalinity required? What is the answer? We need 214 milligram per liter of alkalinity. We have 240 milligram per liter in our wastewater. So additional dose of alkalinity required is 0. So the answer is 0. You got it? So read the question clearly. 7.14 milligram of alkalinity is required for ammonia to nitrate conversion. Our wastewater have 30 milligram ammonia, 240 milligram per liter of calcium carbonate as alkalinity. They ask what is the additional dose of alkalinity needed. Other data you please leave. Then only you can identify easily. You got it? With the same data, the second question is, this here the zero alkalinity is answer. Second question is, assume the density of oxygen is 1.91 kg per meter cube. What is the amount of oxygen required? Because this process is aeration process. Nitrification process, aeration process. Denitrification process is anoxic process. This is oxic process. So, what is the oxygen requirement? You can do this mass balance again. Ammonia is 14, right? 14 is the ammonia mass. requires 1 mole of ammonia requires 2 moles of oxygen. So 2 into 32 milligram of oxygen. So 14 requires 64 milligram. Second. Fourteen requires 64 milligram of oxygen. So how much nitrogen I am having? Nitrate I am having 30 into 2.5, 30 milligram per liter into 2.5 into 10 power 6 liter per day. So liter will cancel, milligram per day. So that much milligram of oxygen I will get. This milligram will cancel. So as per my mass balance, 1 mole of nitrogen requires 2 moles of oxygen. So 1 mole of nitrogen is 14, requires 64 milligram of oxygen. 14 gram or milligram, whatever. 14 gram of nitrogen requires 64 milligram of oxygen. So I have 30 milligram per liter into 2.5 million liter into 10 power 6 liter of nitrogen requires how much? So just cross multiply, you will get 30 into 64 divided by 14. 64 divided by 14. How much? 30 into 2.5 into 10 power 6 divided into 64 divided by 14. That is in terms of gram or kg. If you convert into kg divided by again 10 power 6. 342.8 kg of oxygen required. They are asking in meter cube. I am provided with kg per meter cube density. So if I divide with 1.91, I'll get 179.5 meter cube per day. Initially it was in kg per day because there is a day here. Are you getting? It is correct. 342 is correct. Then convert it into meter cube. Meter cube per day by dividing it with 1.91. What you are getting? 179 or 180? Are you getting 180 meter cube per day? That is the answer. Are you getting? Yeah, done. So this is the simple conversion. 1 mole of this requires this much of oxygen, or 1 mole of nitrate is ammonia is converted into 1 mole of nitrate. This kind of things you can follow. Same question, daily amount of sludge produced. They said 1 nitrate produces, sorry, 0.15 milligram of sludge will be produced from 1 milligram of nitrate. So they already clearly mentioned 30 milligram of ammonia. So that will produce 30 milligram per liter of nitrate. That will produce into 0.15 milligram of sludge. You got it? So 30 into 30 milligram per liter into 2.5 into 10 power 6 liter per day of what we say ammonia will be forming the same quantity of nitrate because 1 mole same quantity of nitrate adula 0.15 will be my sludge. How much it will be in terms of divided by 10 power 6 you will get kg, milligram will get kg. So 10% 10% cancel, 30 into 2.5 into 0.15, 11.25. Are you getting 11.25 kg per day of sludge? That is correct. Yes. Can just I will move again with the 10 questions. It will be very easy. Please follow me. Typically, advanced treatment of wastewater is carried out before biological, during biological, after disinfection. Advanced treatment. Yeah, C is correct. But I have one check here. Advanced oxidation process will be followed before biological. Okay, please remember because whatever the recalcitrant organic, we can do some AOP process to make it biodegradable, then we can do biological treatment. So advanced oxidation process can be used before secondary treatment, but advanced treatment, all the tertiary treatment can be done after biological. You got it? So tertiary and advanced beyond secondary treatment. Okay. Pollutant or contaminant that can be removed by advanced are called recalcitrant, nutrient, dissolved metal, all the above. This we already seen. So all this can be removed with the tertiary treatment. Here, nitrogen removal, which method? Phosphorus removal, which method? Dissolved solids, which method? All know dissolved, total dissolved or TDS can be removed with the reverse osmosis. Nitrogen can be removed with the gas stripping, that is ammonia stripping we had seen, right? One of the chemical method. Lime is used to remove to increase the pH, that will directly convert the ammonia in the aqueous form to ammonia gaseous form, right? So that is the chemical nitrogen removal, gas stripping method. Phosphorus removal by chemical method, again alum and lime addition. So what is the answer? A1, B3, C. Correct? Yes. So nitrogen removal by ammonia stripping. Phosphorus removal by lime and alum. Reverse osmosis for TDS. High 95% of dissolved solids can be removed with RO. Identify the correct statement. Typical municipal wastewater effluent majorly contain ammonia, nitrogen, organic nitrogen. Is it correct? What are the nitrogen form in typical wastewater? Ammonia, nitrogen, and organic nitrogen. Yeah, this is correct. Then nitrification and denitrification can remove by precipitation of nitrogen in the form of sludge. No. Chemical treatment will form precipitation. Nitrification and denitrification will oxidize and reduce the nitrogen. So this is wrong. Ammonia stripping is a biological method. That is wrong. Ammonia stripping is a chemical method. It will add lime to increase the pH. It's a chemical method. There is no biological here. Then for the nitrogen removal, nitrification should be carried out in an anaerobic environment while denitrification in an aerobic environment. That is wrong. Nitrification in aerobic followed by denitrification in anoxic or anaerobic. So first statement only correct. A is correct. Got it? So nitrogen removal, typical nitrogen is in the form of ammonia and organic nitrogen. Some nitrate and nitrate will be there, but negligible. This is the major form. Nitrification is the oxidation process. Denitrification is the anoxic process with the addition of excess carbon source. This will act as the electron acceptor. Carbon will form as the heterogeneous source, energy source. Okay. The conversion of ammonium to nitrate through nitrite is called ammonia, or addition of oxygen to nitrite, then nitrate. This process is called nitrification. Yeah, that is correct. Then it will be denitrified to nitrogen gas. So this two addition directly converted to nitrogen gas is called Anammox process. Direct conversion of ammonia to nitrate is called there is no process. Okay. Yeah, this is the process. Nitrification through nitrite. Activated carbon based adsorption units are regarded as a highly effective for the removal of activated carbon, can be used to remove microbial contaminants, nutrients, alkalinity and hardness, pesticides. This is through ion exchange. Nutrients is through chemical and biological methods. Microbial contaminant cannot be removed with the activated carbon. Pesticides is the one having 95 to 98% removal with the activated carbon. Answer D is correct because we had seen lots of pesticides, right? 98 to 95% removal. Some organics will be removed, but microorganisms poor removal. Metals and all, ions and all cannot be removed. Which of the following is not a method of disinfection? Chlorination, ozonation, UV radiation, ultrafiltration. Which is the answer for not a disinfectant? Disinfectant is used to remove the microorganism. Chlorination, ozonation, UV radiation, ultrafiltration. What is answer? D. Yeah, D is correct. D is the wrong answer. Okay. Okay. Regeneration in adsorption and ion exchange refers to what is regeneration? Treating the adsorbent to be reused for another cycle. It is correct. Recycling of effluent. That is wrong. Extracting the retained contaminant in the solid phase for a metal recovery. That is wrong. Electricity recharging. That is wrong. So treating the adsorbent or the ion exchange medium for another cycle is called regeneration. So A is correct. So reactivation is the process of resin is using a strong acid for cation or caustic solution for anion to make it suitable for next cycle is called regeneration. A potential disadvantage of phosphorus removal by chemical precipitation. We have nutrient removal, nitrogen and phosphorus removal both by biological and chemical methods. But the chemical method of phosphorus removal requires requires alum and lime, but it is problematic because it generates high volume of sludge because it's flocculating. Whatever the lime added, that will form flocks and it will settle. So that huge volume of sludge is the problem. Generation of high volume of sludge. See, chemical method we can use, biological method we can use, but chemical method expensive and also costs a sludge volume of up to 40%. So that's the problem with the chemical phosphorus removal. Here, which of the statement is incorrect regarding the adsorption? Both physical and chemical adsorption are exothermic. It's correct. Physical adsorption is irreversible, while chemical adsorption is reversible. It is wrong. Physical adsorption is reversible because it's weak van der Waals force. Chemical adsorption is irreversible because it's a strong chemical bond. The energy generated during chemical adsorption is typically higher than the physical adsorption. Yeah, both will be exothermic, both will exert energy, but chemical adsorption energy generation is higher. So, incorrect statement is B. See, so 0.1 kilocalorie is 10 kilocalories per mole. Identify the incorrect pair. Ion exchange, uncharged organic impurities, carbon adsorption, refractory organics, alum flocculation, nitrogen to ammonia. Think about, don't make confusion. Carbon can absorb refractory organics. That's correct. It dyes, pesticides, we can be removed. So it's correct. Alum and lime can be used for not nitrate to ammonia, ammonia to gaseous ammonia, liquid ammonia to gaseous ammonia. But also phosphorus removal we can use. Ion exchange we can use for uncharged inorganic compounds like chlorine, salt, any salt if you take that is a charged in inorganics only, right? So this is also wrong, this is also wrong. Both A and C are correct. So incorrect pair. The answer is both A and C. You got it? Ion exchange is for dissolved inorganic. Dissolved is charged. Charged ionic impurities. Inorganics. Activated carbon can be used for recalcitrant refractory organics. Alum flocculation is for phosphorus removal, also for nitrogen, aqueous ammonia to gaseous ammonia. See the match the driving force with the membranes. Pressure driven is reverse osmosis. Electric potential driven is membrane electrolysis. Temperature gradient is membrane distillation because distillation will use hot to cold, right? So 213. Answer B is correct. Yeah, it's correct. Pressure driven, concentration driven, electrostatic potential driven, temperature driven. We will solve some problem on 2-3 problems. Very easy. A membrane. So membrane, I am writing a membrane. 700 milligram per liter of TDS is coming in. That's the pollutant. TDS is the pollutant solid, dissolved solid. 30% reject. 30% does reject. So how much coming in? 100% is coming in mass balance. 70% does pure water. What would be the approximate reject to 2200 milligram per liter TDS? Okay. what is the approximate TDS of the permeate, that is the pure water. So inlet, reject, permeate or pure water. So they are asking the TDS of permeate is X. Again do the mass balance, summation of mass in equal to mass out. What are the mass in? 100% of 700 is coming in. You can replace with any value, 2000 liters, 3000 liters, but I am taking as 100%. 70% of unknown value plus 30% of 2200. Can we solve? 100 into 700 minus 30 into 2200 divided by 70. Are you getting 57.14? Answer is 57.14. Not B. Are you getting? Yeah. So the answer is our pure water contains 57 milligram per liter of salt. So from 700 we have reduced it to 57. That's the objective of reverse osmosis. Okay, 57 is the answer. This question you see, 620 liter per day of wastewater containing chromium. Okay, we are treated with the 2.5 gram per liter of activated carbon. So activated carbon they are putting in powder per liter. It's not packed. We are putting a treatment system coming with treating 620 liter per day. I am adding activated carbon 2.5 gram per liter of water. Remove 82% of contaminant in 3 hours. So only 18% is coming out. The final concentration after treatment is 1.5 milligram per liter. What is the pollutant? Chromium. Whatever pollutant you can take. So chromium is coming in. I don't know how much is coming in, but 85% is removed, but only 18% is coming out. That is 1.5 milligram per liter. They are asking what is the original concentration. So 18% is 1.5. 100% is how much? What is the inlet concentration? That's what they are asking, right? 18% is 1.5. What is 100%? Are you getting 8.3 milligram per liter? 82% removed in the system. Only 18% is coming out. That outlet is given as 1.5 milligram per liter. Then what is the inlet concentration? That is 100% is coming in. How much it is? 8.3. Are you getting 8.3? Any doubt in this? Okay. Hope you don't have any doubt. Are you working out or let me move on? Are you getting 8.33? Divide 18% is 1.5. Then what is 100%? So just divide it. 18 by 100, 1.5 by x. So x will be 1.5 into 100 by 18. Are you getting 8.33? That is 8 milligram per liter. Yes. Finally, the approximate quantity of activated carbon required, we are saying 2.5 gram per liter. We have 620 liter per day. So how much kilogram of activated carbon required per day? So 1 liter requires 2.5 gram. 620 liters require 620 into 2.5. That is 1550 gram of activated carbon per day. But in kg, 1.55 kg, right? The answer is 1.55 kg per day. Are you getting 1.55 kg per day of activated carbon required? Final question is the solid phase concentration of chromium. Solid phase concentration is we are removing 82%. Only 18% is coming out. That is 1.5 milligram per liter. we already found the inlet concentration is 8.8 milligram per liter of chromium. So out of 8 milligram, 82% is adsorbed to the carbon. So the solid phase concentration, the removal efficiency is QE, we will say. In adsorption, we will always use the adsorption capacity as QE. Inlet concentration minus outlet concentration. That is the 82% removal into V by M. So that is a formula. Or you can say this much is removed by this much quantity of activated carbon. So how much quantity of activated carbon I am using? That is the mass of adsorbent 1550 gram of activated carbon. Volume is 620 liters of volume. What is the removal? From 8 to 1.5. So 8 minus 1.5. So remember this formula, CI minus CE or FNCE into V by 1500. So 8 minus 1.5 into 620 divided by 1550. Answer is 2.6 milligram per gram. This is in gram. Is this in milligram? Yeah, this is in milligram per liter. Liter will get cancelled. Are you getting 2.6 milligram per gram of chromium in the activated carbon after treatment? So this is the formula, Ca minus Ce into V by M. If you want to convert into milligram or that one, based on 1000, you can multiply or not, you can use. Okay. So thank you so much for joining today. If you have any doubt, you can unmute and you can ask. Don't forget to give the assignment on Wednesday, before Wednesday, and we will meet next Monday 6 to 8 p.m. for the 10th week session. Thank you so much for joining. If you have any doubt, you can ask or you can leave the meet. Thank you all.
Thank you, sir.
Thank you. Thank you. Thank you for joining. We'll meet next week. I'm closing the meet. Thank you all.